Hello, today I'll be telling you about geometry types and giving you a brief overview of how they apply to graphics programming. My name is Dietrich Geisler, I'm from Cornell University, and this is joint work with Irene Yoon from University of Pennsylvania, Aditi Kabra from Carnegie Mellon University, and Horace Hay, Yinon Sanders, and Adrian Sampson from Cornell University. Graphics programming is becoming more and more common. It includes everything from animated film to video games, to computer simulation. Unfortunately, graphics programming introduces a variety of new bugs that make it extremely difficult and has not received this sort of attention that from programming languages experts and programming languages that these new bugs entail. Specifically, suppose when I went to write some graphics programs, I wanted to make a lighting model and some simple shadows. And instead, I ended up with something that looked like this. Something clearly went wrong, but figuring out what that thing is very difficult. You have to kind of stare at the program. And as we'll see, it can be very challenging to narrow down where in the code an error occurred. What we propose is that there's a specific kind of bug that shows up frequently, is pervasive in graphics programming, called a geometry bug. And we propose that these geometry bugs can be caught with something called a geometry type. So what is a geometry type? A geometry type is when we take a simple type, say a three-dimensional vector, and we describe how to represent the object geometrically. So for example, we might represent a position or a point in Cartesian space in the model reference frame. In total, these geometry type consists of a coordinate scheme, a geometric object, and a reference frame. So let's see these geometry types in action in a language we made called Gator. So right now, here's an example of a buggy program, a buggy graphics program. You have this is trying to make shadows appear for the bunny and the teapot, and instead what's happening is that the shadows are like all over the place. They're rotating back and forth. They're popping in and out of the ground. They're not behaving as if they're shadows coming from the light source at all. So what's going wrong in code is that this multiplication right here, U model times U light view, is out of order. It needs to be light view times U model. And the reason for that is these transformation matrices have essentially the wrong quote unquote type. They're operating on the wrong reference frames. So what we can do is by introducing a Gator code instead, I'm just going to copy this over. So previously we were in GLSL, a standard programming language, so now we're going to switch over to Gator, which has geometry types. So you can have, say, card3 model point, and then we also have these transformation matrices, which go from model to world or from world to light. At this point, what happens is we get a compiler error. No overloaded function declaration of times matching the types associated with it. In other words, we've tried to apply a multiplication between two matrices in the wrong order. We've tried applying a transformation between two spaces in a nonsensical way. So to fix this, we're just going to reverse the order of these two matrix multiplications. Our compiler is happy with us, and the shadows work. So by fixing the compiler bug, we've actually fixed the program. Gator can also do one better, however, because this is still a fairly complicated multiplication. And by introducing in expressions, we can just say in a position, which is the position we're operating on, and we can say that we want it in HOM of light projective. That is, we want it in the representation of this particular representation while maintaining the same geometric object. And what that means is that Gator will synthesize this code, the same code that we saw previously, and end up with the same result we had before. So we can automatically generate the correct code using in expressions. Finally, I would like to tell you a little bit about our evaluation of Gator as a language, using these geometry types and these automatic transformations. So in Gator, we implemented a series of shaders. As you can see, there's a wide variety, and we have a variety of effects that we can use, and it turns out that these geometry types were very helpful. Additionally, we also measured in this graph where the x-axis is the shaders that we implemented, and the y-axis is the frames per second over a series of experiments for each of these shaders. And what we found is that the Gator average and GLSL average in blue and gray, respectively, were very similar. In fact, statistically, we found that 4 of the experiments were epsilon at a 95% confidence interval had only an epsilon difference. I would love to hear your questions. Thank you for listening to our talk. If you can take a look at our website shown in the upper left, just send me an email or just ask any questions now. And I look forward to hearing your comments. Thank you.